So I saw this problem called split 25 that says if you take the number 25 and decompose it into numbers that add up to 25 and then multiply those numbers together, what is the largest product that you can possibly get? Now, if you want to try this problem for yourself, don't watch the rest of this video because it's a great problem. But what I realized using a little bit of calculus and a little pre-calc thinking is that it's an optimization problem and it connects to a geometric property that squares or cubes or hypercubes. But the idea that in a geometric property, when you have shapes that have equal sides, you are really dealing with an optimized shape. Same thing is true like with a can, and you optimize the volume of a can. Like it actually has these dimensions that are pretty much equivalent to what a cube would have in that length and width and height are all equal. So then that means I need to set up a problem. I need to set up that 25 as the product is going to be divided by however many pieces we want to multiply together. So if I only want 2 addends, then 25 divided by 2 is going to be the best optimized value, because half of this information, which 12.5, will form one edge of a square, and 12.5 will form the other edge or side of a square. And then when you multiply those two together, the area that you get is the largest solution, the biggest product. So similarly, if we form a cube, then 25 divided by 3, of the 3 numbers that add together to make 25, we want them to all be the same, because this information, what is that, 8 and 1/3, that would form your edges of your dimensions of the cube. So 8 and 1/3 by 8 and 1/3 by 8 and 1/3. And then when you multiply all 3 of those together, you would have the biggest product that you can make with decomposing 25 into 3 things and then multiplying them all together to get you your biggest product. So that led me to think about, I want to generalize this. I want to generalize this to what is the largest or optimized, and we could extend this out. I mean, honestly, if we talked about dividing 25 into 25 addends of 1 plus 1 plus 1 plus 1 plus 1, you'd have a volume of 1. And that's definitely going to be smaller than this. This is 156.25. But we can do a little bit of setup with a formula. And so in our formula, I'm going to say I have 25 and I'm going to divide it by some number of addends that we want. But just like the square and the cube, the point here is to multiply that number. That's the same thing as like the edge of the square, where 25 divided by 2 was 12.5 and 25 divided by 3 was 8 1/3, that we're going to multiply this by itself in times, and we'll essentially get the area or volume or hypervolume or whatever we call that term, representing the space in between. It'll be the maximized space of all of it. Well, we could graph this. When we graph it, we get a shape that looks something like this. And because it looks something like this for n values, I'm going to project out here. I don't know what this is. I'm going to say like 20, somewhere in the middle. This is the key thing, is what is that middle? Because when we know what that optimized value is, not only will we know the number of divisors or pieces to decompose 25 into, we'll also get the volume or the hypervolume or the biggest product that you can get from multiplying all of the decomposed addends of 25 together. One other comment, because it's addends, we're going to get a decimal value, but we're going to use the floor version, which is just the integer value, no decimals at the end of it. Even though decimals will exist, we're going to acknowledge that there is a domain restriction, so we are only allowed to use whole numbers for n. Okay, that's the setup. Stick around for part 2.